Welcome back. In this video, we will see two new operations of graphs, and that is the subdivision graph and the powers of a graph. Line graphs will come in the next video. So here we're focusing on subdivision and powers of graphs. And we'll see a nice result about powers of graphs and Hamiltonicity, in particular Hamiltonian connectedness. So we start with a new graph operation called the subdivision of a graph. This is denoted S of G, and it's the graph obtained from G by replacing each edge, so each edge UV, with a new vertex, W sub E, and two new edges, UW sub E and VW sub E. So what does this look like? So here's K4, and what we do is for each edge of K4, here I'm going to build the subdivision of K4. This isn't the subdivision yet. I'm going to plop a new vertex down on each edge. And what I'm doing is I'm subdividing the edges. So when I plop that new vertex down, I'm actually doing more than just putting a new vertex down. I'm removing the old edge between these two vertices and adding two new edges. So this edge and this edge. So in that way, I'm taking each edge and subdividing it and making two new edges out of it, removing the old one, adding two new ones in, along with this new vertex. And this is the subdivision of a graph. So we'll do some stuff with this later. For right now, we'll just note some properties of the subdivision. So if the order of the graph is n, and its size is m, then think about what would be the order of the subdivision. What would be the size of the subdivision? So the order, well, I keep my same vertex set and then I add more vertices. And how many more vertices do I add? Well, I add a new vertex for each edge of the original graph. So the order of S of G would be n plus m. Size of S of G, well, let's see, I had m edges to begin with, and then in each edge I added a new vertex and deleted the old edge and made two new ones. And so the size of S of G should be twice m. Second thing to note here is that the subdivision graph is always bipartite. So this is a way of taking any graph, producing a bipartite graph from it. The partite sets here would be if you select all of the vertices that you subdivided the edges with, so these ones, and then the original vertices of the graph. That would be your two partite sets. You'll never have two new vertices that were added that were adjacent, because you always subdivide an edge and it's just adjacent to the two vertices that were there before that had an edge between them. And then any two vertices of the original graph, well, I've subdivided any edge between them, hence they're not adjacent in the subdivision. And so that shows that subdivision is always bipartite. So that's the subdivision of a graph, and we're going to move on to a new operation. So this is actually a family of operations called powers of graphs. In particular, we're going to look at squares and cubes of graphs. So for any positive integer k, we define the kth power, g super k, of a graph G so the vertex set of g sub k, g superscript k, g to the k, is the same vertex set as G. So keep all the vertices the same, and an edge is in the kth power of G if and only if the distance between U and V in G is between 1 and k. So what we're doing is we're joining up all vertices whose distance is at most k when we complete the kth power of the graph. So we'll look at G squared and G cubed. So here's my original graph G, and here's G squared. So so this isn't G squared yet. I'm gonna just plop down the vertices and the original edges of the graph. We keep along the original edges of the graph, and then we add some new ones because, well, the distance between any two vertices here that are adjacent is 1, and so we keep those as well. And now what we do is we join up vertices whose distance is at most 2 in the original graph. So for example, this vertex and this vertex are distance 2 from each other, so I put an edge between those two. Same with these two, same with these two. Also, look at this one and say this one, that was distance 2, as well as this one down here. Those were all distance 2 from each other, mutually distance 2. And so that forms a triangle. And so the resulting graph, and I think we got all of them, is g squared. Yep, that's all of them. So remember, reference back to the original graph. I don't want to keep doing this, adding distance 2 between vertices. I don't want to do this recursively. I would end up with the complete graph. G cubed, now I'm going to, again, reference back to g. And so one, any two vertices that are distance 2, well, that's at most 3. And so all of the edges from g cubed or from g squared are also in g cubed. So I'm going to add all those in as a first step. And now I also add in edges between vertices of distance at most 3. So 1, 2, 3. These two would be adjacent. Same with these two. 1, 2, 3. Same with these two, and these two, and these two, and these two. And I believe I got all of them now. We should have a... Yep, that's all of them. And that's how you form the cube of a graph. And I say subscript, and I even wrote subscript. G cubed, so used to writing subscripts and not powers. So that's how you form the power of a graph. So our next step is to talk about some results involving squares and cubes of graphs in reference to Hamiltonicity, because that's the theme we're going on. So first is theorem 6.22. If G is a connected graph, then its cube is Hamiltonian connected. So if you raise a graph to the third power, it'll automatically be Hamiltonian connected. That's enough to guarantee it's Hamiltonian connected. I am going to skip the proof of this one. You can read through it in the text if that's helpful for you. I'm going to skip the proof. I just want you to know that this is a thing. If we raise it to the third power, we get Hamiltonian connected. And then we also have this theorem, theorem 6.23, that if G is a two-connected graph, then its square is Hamiltonian. So that's a nice result. And what I'd really like to do is I'd like to take this result. This one is not in the book, by the way. This one takes a bit longer to prove, and so it's not even in the text. Theorem 6.23, right? If you have a two-connected graph, so no cut vertices, then its square is Hamiltonian. So yeah, what I want to do is use this to prove theorem 6.24. So this is the proof I really want to do, because this is a really awesome proof. This was proved by Chartrand, Hobbs, Jung, Kapoor, and Nash-Williams. And so Chartrand told me the story of this theorem, and apparently this was largely Nash-Williams' idea of how to do this proof, but this was in a paper by all of them. So all of their names are on it. And I'm sure they helped out a bit, but this was essentially Nash-Williams' idea. Chartrand always spoke very highly of Nash-Williams, by the way. Okay, so how does this work? So G is 2 connected, and so its order is at least 3, otherwise I could get a trivial graph by removing a vertex. So G is 2 connected, its order is at least 3. I'm not even going to write that down. We're just going to remember that. And let U and V be 2 vertices of G. And we're going to show that there's a UV Hamiltonian path. So we show there is a UV Hamiltonian path in G squared, right? So that's what I'm showing is G squared is Hamiltonian. Okay, so how do we do this? So I'm going to copy G 5 times. We'll call it G1, G2. I don't care what G is as long as that's 2 connected. G4, G5. And I'm going to remember my 2 special vertices U and V. And I'm going to name them in each copy U1, V1 for the first copy, U2, V2 in this one. So these all represent the same vertex in the original graph, G, U3, V3, U4, V4, and U5, V5. And now I'm going to add 2 new vertices in, W1 and W2. And I'm going to join up W2 to all of the V's, all of the copies of V, and W1 to all of the copies of U. All right, so I've formed this new graph. I believe we're going to call this new graph F. So, okay, so I'd like to use theorem 6.23 here, and that's that if G is 2 connected, then its square is Hamiltonian. So I need to show this graph is 2 connected, so that is there's no cut vertices here. Well, certainly neither W1 nor W2 is a cut vertex, and if I had a cut vertex in one of these copies, then it would be a cut vertex in G. If I just looked at G by itself and removed that vertex, it would be a cut vertex. And so there's no cut vertices, and so F is 2 connected. Which means, by theorem 6.23, that it's Hamiltonian. So by theorem 6.23, F squared is Hamiltonian. So there's some Hamiltonian cycle C. Let C be a Hamiltonian cycle in F squared. So remember, this is an F squared. I'm not going to draw the edges in for F squared. This is just F, and know that there's some Hamiltonian cycle in F squared. And I'd like to use this fact now to show that G actually has a Hamiltonian UV path. So W1 and W2 must be visited on this Hamiltonian cycle C in F squared. Remember, this has the same vertex set as F. So W1 and W2 have to be visited, and so there's some edge into W1 and some edge out of W1. Same thing for W2, there's some edge into W2, some edge out of W2. So that's a total of 4 in and outs for W1 and W2. In particular, there's always going to be one component such that no vertex, or not a component, sorry, one copy of G such that no vertex of G is adjacent to either W1 or W2 on the cycle C. So let me zoom out a bit so I can write this down while we're still looking at it. So there is some copy, let's say it's G1. Say G1, such that no vertex in G1 is adjacent to W1 or W2 on the cycle C in F squared, right? Because there's only 4 in and outs. One of these is not adjacent to W1 or W2 on the cycle C. Okay, well, that's interesting. What that means is that, remember, I have some cycle, right? So I guess the thing to picture is here, W1 goes into W2. It doesn't actually have to hit U2 here to go from W1, because again, I'm looking at the square of it. So maybe there's an edge here to some vertex in G2 that goes to W1, and maybe there's one here, and it loops back around, and maybe it jumps over to W2 through here, and maybe it jumps back here, something like this, and maybe it bounces around a little bit, maybe it jumps over here, maybe it jumps back and forth between, well, it can't jump back and forth that much between it, but certainly V4 and V5 could be adjacent, and maybe it goes through here and back. All right, so the point is maybe it does some stuff, but no vertex in G1 is adjacent to W1 or W2 on C. So what that means is, since V1 and U1, in order to get, right, I messed up over here when I said that, right? I can't, any vertex here that's not V4 and any vertex here that's not V5, for instance, they're not distance 2 from each other in F. And so they're not adjacent in F squared. So it's true that, say, V1 and V2 would be adjacent in F squared. Same with U1 and U2. Same with V1 and V3. These would all be adjacent in F squared. So those can all get to the other copies of G in F squared. But no other vertex has that property, right? I can't jump from a vertex in G1 to a vertex in G2 that isn't one of these ones. So the fact that no vertex here, right, so no vertex here is adjacent to W2 on the Hamiltonian cycle, but we have to come in and out of that copy somehow. It means I have to jump from G1 to G2 or G3 or G4 or G5. I have to jump across W2 and get into one of those components. The only vertices that can do that, like I just said, are U1 or V1. So that means there's some edge, maybe I don't want that vertex. So there's some edge on C, like V1, V3, for instance. And there's some edge on C, like U1, I don't know, U4, for instance, something like that. And there's no other edges out of G1 except for those two. So the cycle comes in, and then it has to stay in G1. Jumps between vertices, and it has to exit at U1, or vice versa. It enters at U1 and exits at V1. And so what that is, if I just peel off that part of the Hamilton cycle, well, that must be a Hamiltonian UV path in G. So let me write a few words now down below. I'll say since the only vertices of G1 that are adjacent to vertices outside of G1 and W1, W2, let me look at their nice wording of this. Right, yeah, it follows that by what I was saying up there. It follows that there's some sub path of the Hamilton cycle C. It follows that there is a U1 V1 that there is, I guess I can say on C, there is a U1 V1 Hamiltonian path. U1 V1 path all of whose vertices are in G1. Then this is a U1 V1 Hamiltonian path in G. And I actually can drop the U1 V1. I'm talking about in G now, a UV Hamiltonian path in G. So that's the idea. So this is a really cool technique that they came up with to show that there must be a Hamiltonian path in, oh, sorry, this would be in G squared, not G. All right, that's the end of this video. The next video, we'll talk about line graphs.